So far, we've talked about, we started this class with electron interaction. Okay, we looked at valence electrons, we looked at how electrons interact, and that leads to different types of primary bonds. And then we looked at bonding and crystal structure. So based on the different kinds of bonding and based on the different kinds of crystal structures, you will also have different types of material properties. But so far, when we talk about crystal structure, we're talking about a continuous crystal structure that looks the same everywhere. And that is very, very unusual. We don't have anything. So when you have something that is uninterrupted, it is called a single crystal. Okay, so if we were to draw your crystal structure in a two-dimensional way, your material would look something like this in two directions continuously. No deviation, no breaks in the crystal, and that would be a single crystal. And this is very, very rare. And the really only place that you would be encountering a single crystal is in, does anyone know where that might be? It's in a silicon wafer for integrated circuit purposes. Right, so and we will talk about why it is important for a silicon wafer to be made from a single crystal. And in fact, it's the ability to create a single crystal of any significant size that has contributed to the growth of the silicon revolution, or the idea that you could make integrated circuits and the digitalization of things. Okay, so the ability to grow a large single crystal is really important in that industry. But that's really rare. We don't usually use materials that have a single crystal without any interruptions. What we usually use are polycrystals. And these are materials made of many crystalline orientations, or what we sometimes call these are grains. So if I were to draw something in two dimensions again, it might look something like this. You have a crystal here. You have another crystal here. Is the same crystal structure, but it might be oriented differently. So something like that. So that would be a polycrystalline material. So materials made of many, many grains and not a continuous crystal structure. And so we talked about electrons, bonds, structure as being really important in material properties. I want to introduce to you a fourth item that has a really strong contribution to material properties, and that's defects. So defects also have a strong contribution to material property. And unlike electron interaction, bonding, and crystal structure, all three of those things are not controllable easily by us. It is not easy to change, it's impossible to change the valence electron structure of a material. It is not easy to change the crystal structure of a material, right? Those are things that are inherent to the material. We learn about them to understand why materials behave the way they do and the limitations in where we could control material properties. But we don't really have a lot of control over those. But if you're an engineer, what you want to do is have some control over materials. You want to be able to say, I could do this to make the material stronger, or I could do this to make the material more transparent, or I could do this to make material more flexible, so on and so forth, right? So a lot of that has to do with defects. So defects is the first place where we're going to talk about where we actually have quite a bit of control over the material properties. And there are four types of defects: point defects, linear, planar, and volume defects. So four types of defects. And we'll start with point defects today. So in point defects, you can have things that are called vacancies, substitutions, and interstitials. So if I were to draw a crystal structure, maybe that looks like this. A vacancy is where an atom is missing. Okay, so that would be a vacancy. A substitution is if you have a different atom that's sitting somewhere in a crystal structure that has replaced the original atom, so substituting for that atom. Or you can have an interstitial impurity, so you have something that's sitting in a spot that's not part of your crystal lattice. So vacancies and substitutions occur at lattice points, and interstitials occur in between lattice points. Does anyone know why vacancies? So first of all, there are no materials that have 0 vacancies. All materials have some amount of vacancies. So anyone know why vacancies might exist? Atoms might leave, but why would they leave the structure? Why would this atom leave the structure? Energy, right? So just a reminder of something that we talked about yesterday. This is an energy bond diagram. Okay, and we know that our average bond length. Okay, so as you increase the energy of the system, the atoms vibrate. And if you give it enough energy, some of the atoms are going to have far enough, a long enough bond distance where they're no longer interacting with each other. And so that atom can escape. And even at low temperatures, so you need to remember that, have you studied thermodynamics? Like, I know you have because you're graduate students. But what about the freshmen? Is thermodynamics something that you've heard about in physics, maybe? No? Not really? Okay. You will learn about it. Thermodynamics is a really important part of any engineering and science, actually. But basically, there are many parts of thermodynamics. But one of them is that it's a probabilistic way of looking at things. So when you're talking about the temperature of 25 degrees Celsius. Not every atom at 25 degrees Celsius is moving at the same speed or have the same vibration. It is an average. So some are moving faster, some are moving slower. But on average, at 25 degrees C, atoms have a certain speed, depending on their bond, depending on this diagram, right? So even at low temperatures, there are going to be some atoms that are just going to have enough energy to escape the bond energy. The higher the energy, the amount of energy you supply, the more atoms will be likely to have that energy to escape. The lower the energy, the fewer atoms will likely, or it'll be less probable for atoms to escape. Higher energy will be more probable for atoms to escape. But it doesn't mean that it's a all or nothing kind of thing. It's not like either all of the atoms escape or all of them stay. Okay, it's a range. It's a probabilistic curve that you will see. And so thermodynamic reactions are represented by an equation. In our specific case of looking at number of vacancies, we use this equation. Or you could write it like this. N sub V equals a number of vacancies. N equals the number of sites or atoms. Q, activation energy. So how much energy does it take for an atom to break its bond and leave the structure? T is temperature. K is Boltzmann's constant. 1.38 times 10 to the negative 23 joules per atom degrees Kelvin, or 8.62 times 10 to the negative 5 electron volts per atom Kelvin. So if we were to look at this equation, what will happen to the number of vacancies if my temperature increases? If you look at this equation. If my T goes up, my n sub v goes up or down. So this is to an exponent. T is on the bottom, but it's a negative. So if everything else stays the same, the K is a constant, Q for activation energy for any given material is the same. The number of atomic sites should also stay the same. So if T goes up, the number of vacancies go up. And if you're not sure, you could just plug in some numbers and see, right? It's always easy to just try a couple numbers and see what happens to your n sub v. If you were able to change the activation energy, let's say you increase your activation energy and you keep T constant, would n sub v go up or down?
Down.
Okay. All right. If you were to increase the number of your atomic sites with your n sub and keep everything else the same, would you expect your n sub v to go up or down? Very good, up. Okay, that's by looking at the equation, but thinking about it, hopefully it makes sense, right? The more energy you give a system, the more likely or probable you will have atoms that have enough energy to leave or to break the bond, so you should have more vacancies. If you were able to increase the activation energy, you're making it more difficult. Atoms would need to get more energy in order to break the bond and leave the structure, so the number of vacancies should go down. If you have more atomic sites, but the probability of leaving the system is the same, but same probability times a larger overall number of sites means you should have more vacancies as well. Okay, so hopefully this equation makes sense to you. And I'm usually a person who does not like to ask people to memorize equations because you can look up almost any equation, pretty much every equation you could look up online. I want you to understand the equations. I don't really want you to memorize them. But if you were to memorize any equation from this class, I would say this or a version of that equation is something that's really important to know. And that's called Arrhenius equation. So it can be written like this. Okay, C is a reaction rate. So something that depends on temperature and energy. So it's C. A is a material constant or a constant for the system. E of A equals activation energy. And R is the gas constant. So you can see that our equation for number of vacancies is just a version of the Arrhenius equation. The Arrhenius equation describes many, many, many systems. You could use it for anything where the reaction rate or what you're expecting to change is dependent on temperature. Because for any system, if you want change, there's some sort of activation energies. You have to put energy in order to change that system, and that is temperature, and temperature is a way to provide that energy. So anything that can change based on temperature can be described with this equation. So it's a really useful equation to know. But how do we, besides being really useful, it's actually really practical as well. We actually use this equation to figure out a lot of things that may be difficult to find out about different systems. So if we look at this equation and we take the natural log of both sides, we get this equation, right? And if you were really good at geometry, you might recognize this as an equation of a line. The y-axis, the x-axis, the slope, and the y-intercept. Right? That's the equation for any line. So if we were to plot this according to the equation of a line, then our x would be 1 over t. Our y-axis would be natural log of the reaction rate, whatever is changing. Would you expect the line to have a To go down or to go up? It's a straight line. So would you expect the line to only, or flat? Flat, up, or down? Okay, I see several of you pointing down. Why down? Yes, because our slope is a negative here. So our slope is negative E of A over R. And where this line crosses the y-axis, that would be our natural log of A, because that's a y-intercept. So let's say you were wondering, how do I know the activation energy for a vacancy in iron, in the BCC form? How would you measure that, you think? What would you measure? If you're trying to calculate for the Q, activation energy for a vacancy for iron, or gold, or copper, some element, how might you be able to measure that? How did they find that in the first place? How were they able to determine the activation energy for a vacancy? So it's related to this graph, right? That's why I'm talking about it now. Yeah, if you do an experiment and you could somehow figure out this line, then you could look at the slope. And because the bottom here, K, is a constant, the slope would tell us the Q. Okay, what experiment might you be doing to find this line? So I would vary the temperature, right? Because this is, the x-axis is 1 over T. So if I change the temperature, that gives me one of the variables. What would you do to figure out the y? The y would be the natural log of the number of vacancies. The volume decrease or like change, the volume change. The vacancies are not necessarily related to volume, right? Because if you look at this, if this atom leaves, your volume doesn't necessarily change. What might change instead of the volume? Density or weight, right? The weight, the more atoms leave, the lighter the material might be, or the less dense. And the fewer atoms, so you would be measuring density, weight, something related to that you measure as you change the temperature. And if you have a line like this, then you get the activation energy for creating a vacancy. And then where that line crosses the y-axis would give you the number of atomic sites that your material had. And then you could double check and see if that makes sense with the volume of material you have. So this equation is really, really useful because it gives you a very simple experimental way to determine many different kinds of activation energies and system constants. So that's one way of adding energy into a system for vacancies to happen. What are some other sources of energy to create a vacancy? We know we have temperature. Any other way to add energy into your system to create vacancies? We mentioned that defects are something that we can control, right? So we could control the temperature. That will control the amount of vacancies. What are some other ways that we might be able to add energy into the system if we wanted more vacancies? Pressure, okay, so mechanical, right? Either you press on it, you can bend it. Anytime you add mechanical things to a system, you're adding energy. So mechanical energy. Any other way to introduce energy into a system? If you run a current through it, right? You're adding energy, so electrical. And then the last one is chemical. So these are all different sources of energy for any system, not just for materials. By using those, you could change the number of vacancies or add different amount of energy into your system and change the number of vacancies. So now let's look at, I'll talk a little bit more about substitutions, but first I wanted to talk about interstitials. So let's say we have iron in the BCC form. In order to make steel, does anyone know what steel, the composition of steel is? It's mostly iron with a little bit of carbon. So now we want to add carbon. And let's say we want to keep the BCC structure of the iron. So we would have to add the carbon into either an interstitial site or a substitutional site, right? So let's figure out where carbon would fit. Based on looking at this crystal structure or unit cell, where do you think would be an interstitial site? What is the space that might exist between the lattice sites? So where might the carbon sit in a BCC unit cell? So it might sit right here, right? Or on the top here. So let's calculate how big that interstitial site is so we could figure out whether carbon will fit in there or not. So if I were to draw the 1, 1, 0 plane, it's going to cut through the body center here, so you have the atom, and that would be here. Any questions so far? I would like you to calculate the size of that interstitial site. So what is R? And I will give you some. So the size of an iron atom, it's around 0.17 nanometers. So how would you calculate the size of the interstitial site? So go ahead and work on that on your own, or you could work on it with your neighbor if you want to talk to someone about how to solve this problem. And then I'll give you a couple minutes, and then I'll ask you for what the answer you got. Anyone have any numbers yet? 0.0. What's the unit? Nanometers. So if no one has a different number, does anyone have a question about how we got 0.026? So looking at this diagram, I could say that there might be another interstitial site, right? Maybe along the edge here. What is the size of that interstitial site? Can you do it without calculating, or do you need to calculate again? Without calculating, because it's also A equals 2R plus 2 small r, right? So it should be the same. So you have two different places where you can have these interstitial sites, along the face centers or along the edge centers, but they're the same size. All right, so what is the size of a carbon atom? So where would the carbon go? If we say, well, I'm going to use the red or pink as my carbon, and let's assume the white is iron, and if my carbons were to go into the substitutional sites, imagine all the white ones are the same size. All right, so there are two possibilities. My carbon could go into the substitutional site. This is not ideal because carbon is a lot smaller than iron, right? So there's a size difference, and the bonding would not, the R would not be at the minimum possible energy. We know that there's an energy bond length diagram, and that there's a minimum energy for any system. Because carbon is smaller, it'll be further apart, therefore it's at a less stable state. Okay, so this is not ideal. This is not ideal either. Carbon doesn't fit into the interstitial site without disrupting the lattice, right? We know the carbon is bigger than our interstitial site size. And so by squeezing a carbon into the interstitial site, the iron atoms will need to move out of its space. And now this iron is closer to this iron atom, and so that's also not ideal, right? We want to be at the minimum if possible. By pushing atoms closer, you're at a higher energy. By moving atoms further apart, you're also at a higher energy. So carbon actually could go into a couple of places. Carbon does go into the interstitial sites of iron, but only very, very few, a very small percentage, a lot less than 1%. So you could squeeze a few carbon atoms into the BCC structure without the iron changing its BCC structure. But you can only put a few in there like that. If you wanted to add more carbon, you'll actually need to change the structure. It will no longer be BCC. because it needs to reorganize in order to fit more carbon into either the interstitial sites or a different phase, like a FCC or some other crystal structure. And so we will talk about the carbon-iron phase diagram later in this class. But remember that this is the reason why there are different phases, is because by adding carbon, you're changing the material property, which is something we want, right? By adding carbon, just a little bit of carbon into iron, you now have something that's a lot less easily corroded, right? It has a much better corrosion resistance. It is more ductile, so iron by itself is brittle, or fairly brittle. And by adding carbon, you have more ductility. It can bend without breaking. So you can get a lot of really good material properties by adding carbon. But by adding carbon, you also end up changing its structure. All right, so this is the kind of question I usually like to ask on my exams. And the reason is because for me, this is covering a few things. It's covering your understanding of a crystal structure, your understanding of a unit cell, and concepts of defects, interstitials versus substitutions, that kind of thing. So what if you have iron in the FCC? Okay, this is your FCC iron. Where do you think would be a good interstitial site for this structure? Where do you kind of see space? In the middle of the crystal structure, right? Okay. So can you figure out what's the size of the interstitial site if it were in the body-centered position of a FCC? So find for this structure. So this is how I would start. I would look at the 200 plane. Does anyone remember where the 200 plane would be? 0 and 0 means it's parallel to the y and the z. It intercepts x at the 1/2 position. So this is middle. And if I were to draw it's touching. The size of our iron atom is still the same, 0.17. Anyone have a number yet? Like that? Okay. Anyone get something different? Okay, everyone agrees 0.07 nanometers is the interstitial site for FCC? Yeah? Okay. So carbon actually fits really well into the FCC interstitial site, right? Doesn't fit so well into the BCC site, but our carbon is around 0.07 nanometers. But carbon fits really well into the FCC site. So it's much easier to put carbon into the FCC structure than it is to put it into the BCC structure. BCC, it doesn't quite fit in the substitutional site and doesn't quite fit into the interstitial site. But in the FCC, it fits really well into the interstitial site. Okay. But I have a question for you. We know that FCC is a closed packed structure. It has the highest atomic packing factor of all the different crystal structures. So why would it have a larger interstitial site than a BCC, which has a lower atomic packing factor? Okay, very good. So in the FCC, there is only one interstitial site inside each unit cell, right? Just in the middle of the body center. You might have other places like these corners, but they're going to be much smaller. You could calculate them if you want, something that can sit in here. But you have one big empty site in the middle. For a BCC, you have the 6 faces Each one is shared by 2 unit cells. So 6 face interstitial sites times 1/2 equals 3. Plus you have all the edge sites, right? You see that there's the same size interstitial site in the edges, so you also have these. How many of them are there per unit cell? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. And each one is shared by how many? 4. So 1/4. So you have a total of 6 interstitial sites. They're smaller, but there are more of them. All right, any questions about point defects? So you have 3 types: vacancies, interstitials, substitutions. And by manipulating the defects, you can actually, the number of interstitial substitutions or vacancies, you can change the material properties. Next week, we'll talk about other types of defects.